than 4 generations ago, transportation was neither better nor faster than it was 4,000 years ago. The Conestoga wagon still was the last word when the winning of the West began. Industry was not much farther along than transportation. Men still had only primitive tools to make the weapons and implements they needed for the work of opening up a new continent. But civilization rolled west on such wheels as these, and crude as they were, the wheels were strong and durable, because craftsmen have always appreciated the need for accuracy. Blacksmiths used what was called a traveler, one of the many forerunners of our accurate modern gauges. It helped him make the steel tire fit the wheel. But even with the help of the traveler, the job was a tough one. When we consider the slow hand methods by which the old Conestoga wagons, it is no surprise to learn they cost as much as a modern automobile and took weeks to build. Much of the time and the cost came from the fact that fitting parts together was largely a matter of cut and try. Measuring, sighting, and fitting often had to be done again and again before a satisfactory result was obtained. Uniform high quality and quantity production were both beyond the craftsman's reach. These achievements waited on modern science and industry. Out of research in industrial plants throughout America has come the knowledge to make better products at lower cost. This research work begins with the raw materials, which are required in enormous quantities. More effective ways to use them are being sought all the time. And while this search goes on, the equally important work of testing and retesting the raw materials is conducted endlessly. In making an automobile, there are many complex steps from the raw materials to the complete car. Some idea of this is gained by the fact there are approximately 15,000 parts in a Ford V8. Every single part must be made exactly right and out of exactly the right materials. Each must be made as accurately as if it were the only part turned out in the entire plant that day. Here in the main plant laboratory, standard of quality for materials are established and safeguarded. And here research men try to find out all there is to be known about these materials and the parts made from them. For this, they use many ingenious research instruments. This upholstery, for example, wasn't chosen by guesswork. It will continue to look good for years. The research men know because they put samples of it and of dozens of other fabrics through tests that left no doubt about it. This device is called a phaedometer. It produces concentrated sunshine in the form of ultraviolet rays. If a fabric isn't color fast, it can't get by this test. But wearing qualities, just ask this boy's mother, are even more important. And so, upholstery fabrics are placed in this machine to get a real workout, because the machine never tires out. It gives the sample 6,000 of these scuffing, wearing strokes an hour under constant pressure until they finally wear through. Even the most active little boy couldn't match that. By this test, wide differences often are revealed in the durability of fabrics that look about the same. The same rustless steel that keeps this paring knife bright without polishing gives lasting beauty to the decorative trim of the modern motor car. Rustless steel is bright all the way through. But what of plated and enamel surfaces? If they're deeply scratched, will rust spread beneath the finish? The engineers wanted to know, and so they built this special salt spray room to find out. They gave the room, of course, a door of rustless steel. Here, warm salt spray, even more concentrated than along a windswept tropic seacoast, attacks various car parts in tests that last hundreds of hours. They must come shining through treatment much worse than they're likely to get in actual service. To run quietly, and to keep on running quietly for years, the car's hundreds of moving parts must be smooth. But just how smooth is smooth? Velvet is smooth to the touch, so is glass. These plates, for example, look alike and feel alike, and formerly would have been regarded as identical. Actually, however, one is twice as smooth as the other. This machine tells us that. It is a profilograph, the first ever made for an automobile plant. University of Michigan scientists developed it to enable engineers to do something they never could do before. That is to find out just how smooth really is. They call these pictures profilograms. They show all the irregularities in the surface of the sample, magnified 1,700 times. You see here how much smoother one of the glass samples is than the other. For very close study, the profilogram, in this case that of the piston pin, goes into this powerful microscopic projector. By use of this device, surface irregularities of only 1/1,000,000th of an inch may be measured on all finished surfaces. This information helps in making parts smooth, silent, and durable. The X-ray, as everyone knows, has given physicians a powerful new instrument in the diagnosis of human ills. The same instrument is almost as useful in industry. Let's watch an industrial X-ray photograph being made. The X-rays generated by the tube in this 230,000 volt X-ray machine are so powerful that the entire room is lined with lead, 8 tons of it, to keep the rays inside. As the operator turns on the power, the rays shoot through the crankshaft and photograph the internal structure of the metal. They can easily go through 4 inches of solid steel. Study of the X-ray photographs helps the engineers to know the exact possibilities of every one of the 63 different kinds of steel that goes into the making of these cars. This 200,000-pound compression and tension machine is putting enormous pressure on a single ring gear tooth to test its strength. It is a test worse than any the gear would get, even in the toughest kind of going. The pressure goes up and up, more than 35,000 pounds, before suddenly the tooth gives way. As easily as this housewife wrings out a dish towel, this machine twists up a front axle. The axle, which is made of heat-treated manganese alloy steel, is twisted around and around again for 9 complete turns without a break. This is proof, and impressive proof, of the toughness of this vital part. Because they have stronger, tougher, and more uniform steel to work with, the engineers make car parts stronger and much lighter than was possible a few years ago. This strength enables the parts to carry great loads and to withstand the countless little bends or deflections that would tire out metals of poorer quality. Everyone who remembers breaking a wire, as this boy is doing, knows the principle of fatigue in metal. The materials in cars and trucks are designed to resist fatigue for the entire life of the vehicle. The extra margin of fatigue strength is accurately measured in frequent tests. This tester has been called 1,000,000 miles of rough road in a 10-foot box. By breaking down parts on it, the engineers help prevent breakdowns on the road. Iron and steel, of course, are the foundation of modern industry. And in the last 35 years, more ways to increase the usefulness of these metals have been developed than were found in all the centuries before. Much of this progress is the result of using other metals as alloys in iron and steel. To produce just the kind of metal needed, the metallurgists must control these alloys very carefully. Ford metallurgists have a remarkable method for doing this. They analyze each batch of metal before it is poured. This is about the same on the grand scale as for a housewife to make certain the soup has just the right taste before it is served. This is possible because every metal, under certain conditions, has a rainbow of its own. That is the basis of this newly developed method for analyzing materials. They've put the rainbow to work. Here's how it works. A sample of the molten metal is drawn out of the furnace and poured in a special casting box. The casting is cooled, then placed in a container and sped 1,600 feet through this pneumatic tube from the foundry to the spectrographic laboratory. The steel sample is polished and placed in this 40,000 volt spark gap. The light from the spark goes through this tube to the spectrograph and camera in the adjoining darkroom. The light is broken up into rainbows by this spectrograph, and the lines each metal forms are photographed.